Today we will be discussing Lab 3. The goal of this lab is to find the mass of a black hole using the relationships between net force and change in momentum. To do this, we will use position data of a star orbiting the black hole to create a computational model to find Fnet, Fnet perpendicular, and Fnet parallel of the black hole on the star. I was able to find the final mass of the black hole to be about 10,000 times as massive as the orbiting star. First, I found a method to go about solving the problem. We assume the gravity of the black hole is the only force acting on the star. Newton's law of universal gravitation is Fnet equals gravitational constant multiplied by mass 1, the mass of the star, multiplied by mass 2, the mass of the black hole, divided by the distance squared. We can rearrange this to solve for the mass of the black hole, and using given values we can calculate all the required variables except for net force. I then decided to use a computational model to find net force. In the computational model, I will use Newton's second law in the form net force is equal to change in momentum divided by change in time. The net force is the cause of the change in momentum during the time change. Newton's second law also applies to the parallel and perpendicular components of Fnet and dp over dt, which I will discuss further later in the presentation. I will now describe the process I used to find Fnet. I used 3 consecutive star positions over the same time step to calculate 2 velocities of the star. Both of the velocities of the star were multiplied by the star mass to create 2 star momentums. The difference between the 2 momentums was taken to find change in momentum. This was then divided by change in time, and dp over dt was set equal to Fnet, as was established by Newton's second law. This process was put in a loop and run for all series of 3 consecutive star position points. Net forces were calculated for each position point, and when each net force and position was placed into Newton's law of universal gravitation, approximately the same mass of the black hole was calculated. This mass was approximately 10,000 times as massive as the star. Discrepancies in the calculated mass from position to position are due to errors in the observations of the star position, which was minimized in this theoretical example. In addition to Fnet, I calculated the parallel and perpendicular components of net force. Fnet parallel is the force that causes the object's change in speed and is equal to dp dt parallel, which is the change in speed. To find Fnet parallel, I first found the unit vector of momentum. I then found the derivative of change in magnitude of momentum. I multiplied these 2 values together to find dp dt parallel, and using Newton's second law, set dp dt parallel equal to Fnet parallel. Fnet perpendicular is the force that causes a change in direction and is equal to dp over dt perpendicular, the change of direction. Because the perpendicular and parallel components together equal the total net force, I calculated dp over dt perpendicular by subtracting the parallel component from the total net force. Again, in accordance with Newton's second law, I set dp over dt perpendicular equal to Fnet. All of these calculations were put in a loop, and Fnet parallel and perpendicular were calculated for all position points. These values were used to create this model, which visualizes the net force and components over time. The yellow arrow is the net force, the blue arrow is the Fnet perpendicular, and the black arrow is the Fnet parallel. As we assumed gravity of the black hole was the only force in our model, we can predict the net force is always pointing in the direction of the black hole. Looking at the yellow arrow during the visual, this holds true. Parallel force, the black arrow, appropriately always points parallel to the motion in the direction tangent to the motion at the current position. It is the same direction as motion when the object is speeding up and opposite when the object is slowing down. The perpendicular force always points to the center of the kissing circle, but because the orbit is an ellipse, this will not be the same point as the location of the black hole. Comparing the size of the arrows, the net force arrow is always largest and in the direction between the parallel and perpendicular components. This is appropriate as parallel and perpendicular force add to equal the total net force. Finally, we will address the lab's what-if question. If we replace the black hole with a black hole of a different mass in the same location without changing the star's motion, would we be able to find the new black hole's mass? The answer is no. No other mass would fit the data. With the position data we have, we can only calculate the net force and the mass of the original black hole. No mass other than the original mass would exhibit the same gravitational force or net force, or cause the same pattern of motion and change in the momentum of the star. If we were given new position data after the black holes had been switched, we would be able to calculate its mass, but because we are not, we have no data with which to calculate the new black hole mass.